Hello everyone, welcome back to my YouTube channel. Today we will be going over, again, large language models, and we will be talking about attention in transformers. So for this video we have a couple more sources. We're going to be using the sources Visualizing Transformers and Attention by 3Blue 1 Brown, Attention in Transformers Visually Explained by 3Blue 1 Brown, How Might LLMs Store Facts by 3Blue 1 Brown, Simple Explanation of Transformers and Attention by Codebasics, and Large Language Models Explained with a Minimum of Math and Jargon by Tim Lee. So transformers play a central part in large language models and other AI programs in enabling them to process and generate human-like content. The mechanism of attention stands at the very heart of transformers and plays a significant role in how these models determine contextual word relevance. Although it is central to all of the above, despite its significance, the attention mechanism is usually challenging and complex to grasp. The primary objective of transformer models is to predict the subsequent token within a sequence that involves a comprehensive extent of perceiving word relationships. So attention enables the model to establish word relevance to one another, and in turn, it modifies their embeddings as a reaction. Basically, embeddings are a numerical representation of words retaining semantic value. Using the attention mechanism, words can influence what other words in a context mean, providing the interpretation with depth. For instance, the term bank can mean a money institution or a riverbank, and it is the context in which it occurs that makes one difference over the other. This contextual understanding is made possible through the attention mechanism, which allows words to pass information dynamically to one and to the other. One of the core processes within the attention mechanism is self-attention, which consists of three distinct matrices: key, query, and value. The query matrix is engaged with embeddings to generate a sequence of query vectors. Similarly, the key matrix is used to generate key vectors that are the potential responses to the queries. The value matrix, however, generates value vectors that ultimately decide the final embedding updates. Usually, the same number of parameters are assigned to the key, query, and value maps to ensure balance in the model's processing capacity. These matrices collaborate to make sure that the model is able to effectively identify which words are most relevant in a sequence. Once the attention patterns are computed, they are normalized through a softmax function. Softmax gives the weights to each word to express its relative significance in comparison to another word. It transforms raw attention scores into probabilities that sum up to 1, which makes it easier for the model to realize the relative significance of each word. After softmax, every column of the resulting matrix corresponds to the attention weights for different words, such that the model is able to mark the most informative words while updating embeddings. The mechanism assists in preserving important contextual signals and rejecting less relevant ones. One of the key transformer innovations is multi-headed attention, which allows multiple attention operations to be performed in parallel. Each attention head has its own key, query, and value maps, and thus it is possible to learn different contextual relationships. For instance, one attention head can look at syntactic dependencies, and another one can look at semantic relationships. A model like GPT-3 uses 96 attention heads per block, significantly enhancing its ability to process information. Every attention head produces an embedding adjustment, and these adjustments are added and merged into the original embedding. By the use of multiple attention heads simultaneously, the model has the ability to construct a more comprehensive understanding of language structure and its meaning. Now, data in a transformer model goes through an attention block and multi-layer perceptron, also known as MLP, iteratively. A word comes into the network with minimal context in the beginning, but gets better embeddings as it travels through deeper layers after interacting with neighboring words. This iterative method facilitates more sophisticated contextual representations. Lower levels in the network may have smaller capacities to encode lower-level abstract concepts such as sentiment, tone, and thematic content. Thus, by the time a token has propagated through the end layers of the transformer, it has been endowed with a rich and nuanced understanding of its position in the text. Surprisingly, some researchers have found that the facts are stored in the multi-layer perceptrons of transformer models. The MLPs also seem to have additional capacity for the storage of factual information, which can act as memory banks in the network. The rows of the first matrix of an MLP can be imagined as different directions in the embedding space, each representing different patterns or knowledge domains. The ability to store factual information is useful for language models because it allows them to retain relevant details when answering questions. A lot of parameters in large language transformer models like GPT-3 is taken up by attention heads. However, the majority of them are actually in the layers in between attention mechanisms where embedding gets updated over and over again. One of the reasons why attention mechanism is so potent is because it's parallelizable. Unlike typical recurrent neural networks, or RNNs, which process sequences sequentially, transformers can compute several attention operations in parallel. Parallelism makes training and inference efficient, particularly when done with GPUs or special hardware like TPUs. Word embeddings is one of the main concepts behind transformer models that represent words as numbers in a way that it retains their meaning. There are two primary types of embeddings, static and contextual. Static embeddings like word2vec and glove give fixed representations of words depending on their occurrence in large corpora of text. The embeddings do not change irrespective of the context a word is used in. Contextual embeddings, on the other hand, vary depending on words surrounding them, enabling better semantic representation. Transformer architectures like GPT and BERT rely on contextual embeddings in order to dynamically decode meaning and arrive at a deeper understanding of language. Training a large language model requires vast amounts of text data and an enormous amount of computation. Training involves pre-training from large data, generating input-output pairs from raw text, error calculation, and weight updating using backpropagation. Models are trained to learn not only static word embeddings, but also specialized matrices such as WQ, WK, and WV, which are needed by the attention mechanism. Each training iteration further improves the matrices so that the model becomes increasingly proficient at predicting the next token in a sequence. Now, scale tends to become a significant factor in determining model performance because larger models with more parameters perform better. The training process is to iteratively minimize parameters with the goal of minimizing a cost function, or the discrepancy between predicted and actual outputs. Models get larger in size as the ability to find complex patterns, generate coherent text, and respond more accurately to user requests grows. Scaling does come with such challenges as efficiency in computation and ethics, like reduction of bias and environmental stewardship. In summary, transformers have shaken the natural language processing world with the emergence of powerful mechanisms like self-attention and multi-headed attention. These models gain contextual relationships via efficient capturing, making them process language more accurately than ever. Transformers continue to open artificial intelligence frontiers by continuous training and mass-scale data processing, dictating the language understanding and creation future. Thank you so much for watching this week's video on attention in Transformers. Next week, we will go over reinforcement learning in GPT, InstructGPT, and ChatGPT. Thank you for watching.